what would you need to have the scale? You need the velocity. If we were looking for some quantity whose tangent would give us that information, what might that be? What quantity has a tangent that does give us the information that we seek, as opposed to the trajectory where the information is just the ratio of the velocities?
Tangent on the world line?
Tangent of the world line, which is the speeds. If you have just one dimension, then it's just one speed. If you have it in 2 dimensions of space and 1 dimension of time, you'll have both speeds projected onto the xt axis, the yt axis, and so on. So if you plot the world line gives you the additional information that you need to exactly specify not only the shape, but also the absolute scale. And again, this is a very intriguing problem. So trajectories have some tantalizing properties of geodesics. The trajectories are straight lines and they look like inertial motion in free fall. The trajectory is uniquely specified. Given a tangent, the initial tangent, you can specify the family of curves. If you know just the angle, all you know is the ratio of the speeds. You just know the general shape. World lines, though, have totally the properties of geodesics in that respect. Given the initial tangent, you can totally tell exactly, as you know from solving these problems, if you know the initial speed and direction, then you know the whole thing. And therefore, we would give as a candidate for the straightest line in space plus time, we would suggest the world line of a free fall particle. Now, why is it that to us the world line of free fall particle is curved? Well, because we're in an accelerated frame. Well, we call it gravity, doesn't really matter. And when we're in an accelerated frame, of course, something that's inertial looks curved to us, looks accelerated, no surprise. So we draw it this way. Again, remember, gravity is a field on space, or space plus time, really. So at the moment that they intersect, at that point in space, there is a world line curvature, but it's exactly the same world line curvature for all of them. All right, so a free fall frame has gravitational trajectories that seem like straight lines. You don't feel any gravitational pull. You feel like you're in inertial motion. It seems straight. It's like the straightest possible lines. And an inertial frame, the guy who's standing on the Earth watching you guys fall, he's saying, oh, well, of course, you're accelerated. I can see it. No, he is not a valid arbiter of what is a straight line because he is accelerated. Clearly, an accelerated observer could be looking at some strange acceleration and say that it's inertial. So you can't trust him. If he's feeling inertial forces, he's out. The people falling are not feeling inertial forces. They see everything straight lines. You follow their observation. So therefore, the straightest possible line seems to be a gravitational. Now, gravitational trajectory, almost, not quite. What is the straightest possible line? Not in space. It turns out the arena is space plus time. It's a gravitational free fall world line. If you draw the world line of the particle for a free fall particle, that is the straightest possible line in space plus time. No more inertia. There's no such thing as inertia. Okay? So now, if that's the case, then we're getting the feel that a gravitational world line has more of the properties of straightness in space plus time than virtually anything else. It has all these geodesic-like properties.